Bismillahirrahmanirrahim. Hope you are fine, and here we are going to start with the second week. So before I start this lecture, let me just recall few things from last week. So last week we started with the liquid extraction. We just defined what liquid extraction is, and there were a few basic terminologies about liquid extraction. Then we studied there are various stages involved in its system, and then we switched towards liquid extraction equipment. And in those liquid extraction equipment, there were major two types of equipment. Some are called static, while other are called dynamic or mechanically assisted agitated devices. So after that, now we have to switch towards design of liquid extraction system. But before properly starting with the design, we have to discuss this topic, that's ternary liquid extraction system equilibrium. This is somehow part of design because we have to study equilibrium and we have to apply this when we are going to design a system for this liquid extraction. So I am thankful to few of you who have sent few good questions, and I have answered those, and I hope all other students have been through all lectures and they understand everything properly. But from today now, if you have any question after this lecture, even you can post, or until Saturday similar approach we will follow in all semester inshallah, in which we have to finalize our questions of a week till Saturday, so that I can answer until Sunday, and from next week we have to start with new topics. Right. One thing more which I have observed, it seems that few of you are maybe just going through slides only and they are not listening to the lecture. You see in all of the lecture, I think slides are around 12 to 13, but it takes me like 50 minutes to 1 hour to explain all of those. So definitely there are few things which are just points mentioned in the slides, and you can't get those unless you go through all this recorded lecture. So I will request all of you to go through complete lectures. Also look at the slides, and if you need further assistance, maybe you can go to book. As I already advised, it's better to go through the book. And from today, by the way, this lecture is from section 4.4 of Cedar and Hanley 4th edition, 4th chapter, and section 4.4. So you have to go through that section, because here we involve some problems at the end of this lecture. Hopefully we will quickly go through one of the problem, and later you have to solve the problem. So go through the section 4.4 of 4th edition. Right. So here we will discuss ternary liquid extraction system available at equilibrium, and then there are various types of system. Out of those we have to discuss two which involve like immiscible solvents and then partially miscible solvent. We will discuss in detail what does this mean. So when you will design any liquid extraction equipment, you will need this equilibrium data. You will need some equilibrium calculation. So we have to understand how we can calculate or how we can use those. So equilibrium condition for distribution of one solute between two liquid phases is conveniently considered in terms of distribution law. What does this mean? Actually, when you have to look at any liquid extraction system, you remember that there was a feed, and in feed we said like we consider one carrier or one solvent which is carrying another solute, although that is also in the form of liquid, but that's in small amount. Solute is in small amount while carrier is in large amount. This was feed, and we just bring this in contact with one other solvent which is introduced to remove this solute from feed towards that solvent, and then we finally separate it. So this is actually ternary system which involve two component of the feed and one component which is the solvent introduced externally. So distribution law says that when a solute is distributed between two liquids, What are those two liquid? One is the carrier, which was part of the feed, and other liquid is a solvent which is introduced externally to extract this solute from feed towards itself. So when a solute is distributed between two solvents, its ratio, mean if you look at the ratio of the concentration of the solute between two liquids at the end of the day or at equilibrium, that remains constant. So based on this distribution law, we can look that at equilibrium the ratio of concentration of solute in two phases is constant at given temperature and pressure, and that is given by one equation, that's K is equal to concentration of the solute in extract to the concentration of the solute in raffinate, and while K is called distribution constant. So here when we are saying two phases, now you can understand what are those two phases in liquid liquid extraction. At equilibrium, when we have distributed this solute between the two solvents and then give it some time for the settling, you get actually two phases, extract and raffinate. So extract and raffinate mean this you remember, if you remember that at the end of the settling column, suppose you have mixer and settler, or if you have just static devices, so from the top of the column and from bottom of the column, from the top you get extract and from bottom you get raffinate. Last week we have defined these terminologies. So based on this, you can see that at equilibrium the distribution of this solute into solvents that is given by some law, that's distribution law, and according to that law this ratio of the concentration of solute in two phases remains constant at given condition. Like suppose you are given some temperature and pressure, and if you have to calculate K, it will be constant for any given systems. Suppose you just change temperature, pressure, definitely this will change and then value of K change, but like at one given condition, either you have it in a small amount or large amount, the value of K will remain constant. Small amount, like of small amount of feed, suppose we take only 100 liter of the feed and we are bringing this in contact with like 10 liter of the externally introduced solvent, and you calculate K for that, then you bring like large amount of this feed, suppose you bring like 10,000 liter per hour of feed, and your solvent is also increased from 10 to like 100 liter per hour. So now again the temperature pressure conditions are same, so if you calculate K, it will be same for both cases. This relationship which you have seen here, K mean concentration of solute in extract to the concentration of solute in raffinate, this mean this is applied accurately when both solvents are immiscible. This is necessary for this equation to be applicable, that both solvents should be immiscible. What does this mean? That when you are bringing feed and solvent in contact with each other, carrier or a solvent in the feed should not get should not be soluble with other externally introduced solvent, because if they are soluble in each other, definitely there will be some part of solvent externally introduced solvent with the raffinate, and some part of this carrier will be available with your extract phase. So we do not want to go for such case, so we say this is equation is available or applicable when they are immiscible. And then if there is no association or dissociation of the solute, your solute that does not go for some reaction, that does not dissociate into its part, that remains as a unique identity. Suppose it was ethyl alcohol, so it will remain as a ethyl alcohol, it does not get distributed into the parts. So then this equation will be applicable, because we are saying that in this equation concentration of the solute. So if solute does not maintain its identity, then there will be problem, so you can't apply in that case this equation. But if there is no association or dissociation, then that equation is fine. This is also applicable if your solute is formed of the molecule of different molecular weights. It means actually you have more than one component of the solute. Suppose there is like carrier is water, and we consider that it contains more than one solute which we want to separate from here. Suppose it contains benzene, it contains toluene and xylene, they are available at the same time. So these are actually the different molecular weight components available in this system. And then now solute is like water containing benzene, toluene, xylene. So benzene, toluene and xylene are actually 3 solutes here. So in this case, distribution law holds for each molecular species. Now we will apply distribution law separately on each molecular species if we have such system. Where the concentration of small, the distribution law usually holds provided no chemical reaction occur. Like suppose we just consider that something is available in very small amount, that is almost negligible, or not negligible, or it is in very small amount, like not a large significant amount. So in all those cases, even this distribution law will hold, we can say that that ratio k remains constant for that system, even it contain like small amounts, unless no chemical reaction occur, because if chemical reaction will occur, definitely there will be change in species, and then this will not hold. But as we are going to discuss here ternary system, and we will not be dealing with such system. Ternary system will involve only like 2 components of the feed and 1 externally introduced solvent. Suppose we introduce a new solvent to a binary mixture of a solute in a solvent. So this may lead to several types of the mixture. It means actually when you bring in contact a solvent with a feed, and feed is a binary mixture, that means feed contains 2 components. One is solute, that is actually carried by a carrier, or that is part of a solvent. Suppose just think like you have water that contains acetic acid, and now you have to remove acetic acid. We discussed this example in the first week, if you remember. So water contain acetic acid, and now we have to remove acetic acid from water. So we introduce some external solvent, in that case some alcohol was introduced, I think, and we have removed acetic acid with the help of that. So this, when we add any solvent to a binary mixture, various cases can occur. First, like suppose you can get a homogeneous solution. So homogeneous solution may be formed, and selected solvent is then unsuitable. It means like you introduce a solvent, and you were supposed to remove one component of the feed, like you were doing liquid extraction, but here when you mix them, this solvent and the binary mixture, so what happens in that case, a homogeneous solution is formed. Homogeneous solution that has similar composition throughout like its existence. So in the vessel there will be like at each and every part all 3 components will be available, and they will be in equal amount. So in this case definitely you are not going to get separated these components. So this is one case which can occur. And then there is second case in which solvent may be completely immiscible. So in such case what happens, that when you bring them in contact with each other, so this solute is extracted from feed towards this newly introduced solvent, and when you give them some settling time, they are separated just into 2 separate layer. And we say that in this case, if solvents are like completely immiscible, they did not get dissolved in each other, so you will have 2 separate layer. Then here with initial solvent actually the solvent present in the feed. Okay, the solvent may be partially miscible with the original solvent or initial solvent, resulting in the formation of one pair of partially miscible liquids. Suppose this solvent you bring in contact with the feed, and this newly introduced solvent is somehow partially miscible, means some part of this is soluble with the original solvent, solvent present in the feed. So, in this case when we look at various pairs of miscible liquids, I mean we will discuss this point, that then there will be some part overall you can say that this solvent and the other solvent will also make one pair of the liquid which are miscible with each other, actually miscible with each other. And then there is another system finally where new solvent may lead to formation of 2 or 3 partially miscible liquids. Here in this case actually I mean somehow reactions can take place and finally you get 2 or 3 partially miscible liquids. There will be like somehow no separation, and right when you look at all these types, so among these I mean second and the third are most promising, or which is commonly you come across, commonly used, and out of those even the third one is most common case. So like in second here suppose we can see solvent may be completely immiscible with the initial solvent. So, this is not commonly the case, but somehow it can occur. Sometimes your solvent are not like complete, they are completely immiscible, but in reality this happens usually like your solvents are like partially miscible. So, we have to consider these cases, these two cases, when we are going to design our system or when we are going to look at the equilibrium data. So, here we will consider like a simplest case of liquid liquid extraction with ternary mixers and one stage operation. Actually the simplest is like one stage operation. In one stage one of the student I think have asked this question like what does this stage mean. Suppose I told you like you have a mixer and a settler, so this is one stage, and then you have another stage like another mixer and settler and so on. But when we have like we have to design the system and we have to replace this just this was only mixer settler system. So, we said they are not that efficient. So, we brought some static equipments like there were plate type and there were pack type equipment. So, in those equipment definitely there will be like stages in the form of like those packing or in plates you have, but in simple system we are just looking at this and just consider it like this is a mixer settler system in which mixing and settling is taking place in same unit. So, here you have one unit and in which you are bringing like ternary mixture together. Ternary mixture feed contain two components, you can see here A and B. So, our feed contain two component, while the third component which we are bringing this in contact, that is solvent C. So, overall here C represents our solvent, A and B are two components of our feed. So, when you are bringing them together and then they are getting separated into two phases and they are called like extract and raffinate phase. So, overall you can see that like here when you introduce the feed, so feed contain two component A and B. A is solvent of the feed, or you have studied this with the name of carrier, like that is in large amount here in the feed, and other B is our solute here. You bring this in contact with a new solvent and then you give it some time for the settling. So, after settling you will get two phases, extract and raffinate, and extract is the phase actually that is rich in this solvent, externally introduced solvent, and raffinate is the phase which is rich in carrier A, like here you can see that contains A. Overall in this case actually component A and the C are mutually insoluble, they are immiscible, like the case which we have just discussed, that was the second case in last slide. So, in which they are not miscible with each other, they are not soluble with each other, they are insoluble, mutually insoluble. So, what will happen when they come in contact with each other? This solute B that will be distributed between these two and you get like finally two phases in which like this A is not part of the extract and similarly C is not part of our raffinate phase. So, this is like system which is mutually insoluble. Now, next other case is actually the component A and C are partially soluble in a single equilibrium stage. like when you bring this same feed which contain two component A and B, A is the carrier initial solvent and B is the solute, there you bring this in contact with the solvent mean C, and you give it some time, you mix them, and after settling you will get extract and raffinate phase. So here just look at the component of extract phase. Now you can see that it contains all three, A, B and C. This is extract phase. Definitely it will be rich in solvent component C. So just remember from here, last week you actually have studied this definition that most of the cases extract will be like lighter phase and raffinate will be the heavier phase. But it is not necessary. From now that was okay to start with, but now just remember that extract phase is the phase which is rich in externally introduced solvent. Suppose we are just giving that name of C here. So the phase, now if we just settle them and we look at them, the phase which will be like rich in C, rich in C means that contains C in highest amount, so that is called extract. And other phase which is now rich in like initial solvent, or which you call them A, like here A, so that is rich in A is carrier, that was initial solvent in our feed. So the phase which is rich in feed is called raffinate. From here also remember this definition, please. I will say just remember now this definition, just skip old definition from your mind, that like lighter and heavier phase, because at the end of the lecture when we will discuss one example, so there you can see that actually the densities are switched, like one which is rich in like feed solvent, that is lighter, and other is heavier. So but remember from here that extract or look at that, like extract contain all three component, but out of those three one is in large amount. Suppose for example here I am considering that this C will be like 80% of this stream, so other two will be A and B, and out of those our purpose was to remove B from the A, so second highest this will be B, and then third highest even lowest one will be this A. And if you look at the raffinate, so in this case definitely highest one will be A, then there will be some part of B and then some part of C here. So this system is actually partially soluble. Your two solvents A and C, A was part of the feed and C was a newly introduced solvent, so they are partially soluble in each other. Due to this you can see that they are part of like each other, they are part of extract and raffinate. So we have to discuss this system and develop some equation or some other method to use for design of such system. So let's consider first case, in which first case here first case, this is first case, not the first case of last slide. So that is actually second case of last slide here, but here I am going to talk about this now, first case, and then this will be our second case. We will talk about this later in detail. Actually here I have just explained to you the system. So if you start with this, you can see here like we have one stage here, and B is extracted by the solvent to produce extract E. As I have told you, like here this B is extracted toward this newly introduced solvent, so this phase is actually rich in newly introduced solvent, that was represented with C. And then unextracted B, yes, we have discussed somehow this, that this solute is not 100% extracted toward this solvent, and how we can overcome this problem. Just recall from last lecture, we said due to this we said that we will need more than one stages, because if you are looking for 100% or not, 100% is not possible, but maximum removal of this component B from your feed, you want to just completely remove it, definitely you will need more stages. So here but we have one stage, so overall some part of the B will be extracted, will go with this solvent as extract, while other will remain part of that main carrier, and that will go to the raffinate side. So experimental data for this liquid-liquid extraction equilibrium are often reported in mass fraction instead of mole fraction. So now we have to look at some equations. So just we will be considering some mass fraction and mass flow rates instead of like molar flow rate or molar fraction, because these are liquid, and you know that most of the cases when we are liquid dealing with the liquid, we talk about mass. But if you are going for like gases, so definitely you say something about they are represented actually in the form of mole and mole fractions. So just consider this like FA here is the mass flow rate of carrier A in the feed. This you know, this is the feed, and that contain two component A and B, and out of those we are considering one component A here, that's its mass flow rate is represented with FA. And as we said, this is the system in which two solvents are immiscible. So in this case, any liquid A coming in the feed will be going to only raffinate side. So overall you can say that its flow rate here, flow rate of the carrier A in the feed will be equal to its amount or its flow rate of this carrier in the raffinate. So here its amount coming to this system all will be going towards this raffinate side, because we have considered here immiscible system, totally immiscible system. So in this case its flow rate entered to the system as a feed will be equal to its flow rate in the raffinate side. Just remember this. And then other, just we consider here we are not represented as a Fs. I am actually just using the same terminologies which book has used, otherwise I have represented it with like Fs, flow rate of this stream. So just consider here as a S. So S, we are saying S is the mass flow rate of solvent C. So here this solvent C that has mass flow rate and represented with S. So as this solvent is also not miscible with the other solvent which was present in the feed, which is carrier. So in this case all solvent coming toward this system will be part of the extract. So you can say that its flow rate as enter to the system is equal to its flow rate in extract phase. So from here you can see that when their flow rate remains constant, but at the same time here B, which is our solute which has entered with the feed, that is distributed between two like extract and raffinate phase. So it's if we look for the equation of its distribution or its flow rate in extract and raffinate, so it is distributed, so we have to calculate that. So calculations are facilitated if composition are represented in the mass ratios xi instead of mass fraction x capital. I think you guys remember this when we discussed before this we were discussing absorption. In absorption we have discussed this x capital. So x capital actually if you forgot, kindly go to those lecture and look at this terminology, but I will just quickly define it here. X capital is actually ratio of the mass of two streams. So x capital here mean we are just saying x capital I mean of various streams if we define the x. So we can define it for these systems here also. So our results or equation are more convenient to use if we talk about this capital X instead of small x xi, that was like mole mass fraction. But also if you recall, there we discussed some relationship between this mass fraction and this x capital mass ratios. Just look at those equation in absorption section. But here you don't need those, just we are going to use this mass ratio equation. So for our system we can define two x, one is x capital B. So x capital B is the ratio of mass of solute B to the mass of carrier A in the feed or raffinate. So suppose look at this system back here, you are writing xb. xb we are saying that is the ratio of this solute B, mass of this solute B to the mass of your carrier A. So if you write it like here xb, and then there will be xb for this. They will be definitely different because here mass of B is different and here mass of B is different, but mass of A like carrier remains same. Similarly, another x we are defining that for this system in terms of solvent mass. So that is represented actually with the Y capital here in the book. Actually book is using this as Y, so I am using same, but you can say overall like xb1 and we can say like xb2, like this will be one for feed stream and other is for solvent stream, but just go with the same terminology, no issue. With YB, that is the ratio of mass of the solute B to the mass of the solvent. Now we are just taking its ratio solute B to the solvent. So initially when if I want to write it from the start of the system, at the start of the system, so definitely there is no solute in your solvent C, so this ratio will be 0. But if I look on the other side, extract side, after this liquid extraction, then definitely this will have some value because that solute now is the part of that stream. So mass of the solute B to the this solute in extract phase. Due to this, he just mentioned here extract, but here feed and raffinate, because in that case we can write it for both at the start and at the end of the system, because B was part of both. Like here in this extract side we have only part of like extract phase, we don't have at the start. So I am going to write mass balance equation on this solute C in next slide. So before that, just to clear this, there is some superscript used in that equation, and those superscript F, E and R are mentioned with that. Suppose if we have to write this x B, amount of the B available in like R with respect to feed, and then if with respect to component A, as we said here. So if I have to mention which stream, just recall this when we are writing from stoichiometry, you can recall, or even this absorption section. So if we are writing suppose FA or suppose XA in this feed, so we just mention like which stream we are talking about, because here we have 4 streams, so we have to mention those streams. Suppose if we say feed F, this is represented with like S, and then extract we can represent with E, and if we are talking about raffinate we can represent with R. These are actually the main streams name, or you can say symbols. So overall, if you apply here the mass balance on solute, so you can say that mass of the solute entering to the system will be equal to mass of the solute leaving from the system. Simple material balance, because here input will be equal to output. Because we don't have any reaction here, there is no accumulation, so no consumption. In that case only input will be equal to output, and input that was only part of this, here it was available, B was available in the solute, and then this will become part of 2, extract as well as raffinate. I am sorry, I think here is small mistake. This solute, this will be like B, not C. Solute B, we are applying balance on solute B, and solute B is part of only feed, and then it is distributed into 2 parts. One is extract and other is raffinate. So if I write its equation, that's like solute flow rate in the feed is equal to solute flow rate in the extract plus solute flow rate in the raffinate, as we have seen from the diagram. Like this is simple, input is equal to output. Now output is distributed into 2 parts, due to this we just write it like this way. So here if I have to find the solute flow rate in the feed, that how much is its flow rate, and as we said we have to represent equation in the form of mass ratios. So actually its flow rate can be found from this xb in F. Now we just defined in the last slide xb, so xb was actually equal to xb is equal to mass of B over mass of A. Okay, I am just writing it here for you, but from you can go to last slide and you can check over. This is mass of A. Mass of A is actually carrier, and now we can write it for first we are talking about the feed. So here if I just put F mean, that is representing that I am writing it in feed. So here I will then take mass of B in the feed over mass of A in the feed. So but you need mass of B. So if I just multiply it with sorry, here we are not talking only about mass, we are talking about mass flow rate. So just mass flow rate of B over mass flow rate of A multiply by mass flow rate of this A. So in that case what you can see, if I just cancel these two terms, what I will get, mass of the B. So that's actually my solute flow rate in the feed, mass or mass flow rate, like solute flow rate in the feed. So overall if I just simplify this part, I will get that mass flow rate of the B. So this part is FA is the flow rate of A, and then there is mean flow rate of this A, that will cancel and you will get this mass. But actually we don't need to cancel, we have to represent this equation in the form of these X mass ratios. So hopefully this clear to you now. Then that's equal to outside mean solute flow rate in the extract. So if we look at extract side, so similarly you will write here equation for XB, and as we are writing with respect to like extract, and you know that extract is externally introduced solvent rich feed. So here you will definitely write like YB we defined in the last slide. So that was mass of B over, then there will be like mass of C component here, extract that is rich in C component. So this will be mass flow rate of B over mass flow rate of C, and multiply by mass flow rate of C. Now in that case we have that mass flow rate of C represented with S as we defined in last slide. So here you can write in the similar way same equation, and you will get like mass flow rate of B in extract phase. Because if I want to cancel, what will happen, similarly like first equation here, mass flow rate of C will cancel with the mass flow rate of C, like, and I will get mass flow rate of B. But I have to represent this in this way, so I will just keep it here. And then other B is also part of like raffinate. So here plus I mean you have to write it in the form of raffinate. So here again it will be like mass flow rate of B in the raffinate divided by mass flow rate of B in B over A. So mass flow rate of B in raffinate over mass flow rate of A in raffinate multiply by mass flow rate of A in raffinate. So as you know that in this case mean they are solvents are completely immiscible. So this mass flow rate of A will be equal in raffinate is actually equal to feed. So that's represented with same FA. So here R is representing raffinate, E for extract, and here F for feed means stream where it gets inlet and then it gets separated into two, extract and raffinate. So this is our equation of mass balance on this solute B. So next we just define something which from where we have started our lecture, like distribution constant and K. So that's mean phase equilibrium ratio for distribution of B between extract and raffinate is expressed as, if you remember, there was K and K was equal to concentration of your solute in solute is B. So concentration of B in extract over concentration of B in raffinate. So here concentration of B in extract, E I am just representing with E extract, and B in raffinate. So that was concentration, but here as we are talking about main in raffinate, so initially when we defined it, that K was equal to actually concentration in extract over concentration in raffinate. So but here we are saying something mass ratios. So it will be like mass ratio of that component B in extract over mass ratio of that component B in raffinate. So we have just rearranged it and we took from this here from denominator towards this K, and that K is same constant, distribution constant for this B. So based on this, what you can do, you can just replace YBE in your equation 4.32, this from here 4.33. so if I just substitute this equation 4.33 in equation 4.32, what you will get this equation. So this is finally rearranged equation. Overall just put here yb, so what you will get this k with x term, and that is xbr. so overall when I put it here, it will be like k xb and s term. so overall you can see here xb with raffinate and there xb with raffinate. so just take them common. so what you will get here, if just I take this term common, fa plus kds, and then I just rearrange this equation to in the form of xbr. for some purpose later I have to calculate some value, so you will get this equation 4.34. just write in your notebook and rearrange it, and you will read to this equation. Please kindly ignore these equations appearing here. I will just come here. Divide each terms of equation 4.34, which we just got on the last slide at the end, so by fa. so just look here. if I just by the way, we are just dividing this side, that is its right hand side. so I divide each term by fa. so if I just divide like denominator and numerator by same term, so there will be no effect on the equation overall. so just divide then each term by fa on numerator and denominator side of this right hand side. so what you will get finally this equation 4.34a. this is not available in the book, I have just written it for your convenience. so here you can see that xbr is equal to xbf over 1 plus s k over fa. just look from here please. so if I just divide here, you will get only x term here, and this here will be divided by fa. it will be 1 plus this term divided by fa, which I have written it for you. Now here you can see we have to just simplify this, and this term can be defined in some constant, and that we call like extraction factor. not constant, we call it like extraction factor. This equation is somehow similar, or we are following somehow similar path which you have followed in absorption. so there we also defined or derived such equations. so here this term can be defined as extraction factor. so you can see that extraction factor, that is represented with epsilon, that is equal to this term. so epsilon is equal to k s over fa. so here if I want to increase extraction factor epsilon, so how you can increase it, either you just increase the value of this distribution coefficient. as we said, this depends on temperature pressure, it varies, so that can be varied with changing temperature pressure of the system. and then there is like solvent. if I increase just amount of the solvent in the system, this will increase extraction factor. We will just look how does it help us, extraction factor, or where it helps us actually. and then there is fa, feed. if I just in the feed there is a solvent, that it was flow rate of that solvent carrier. so if I just reduce its ratio or its amount, so it will also help me to increase this epsilon extraction factor. so just put this value from here, equation 4.35 epsilon, in this equation 4.34a. so if I just put it there and I rearrange this equation, what you will get here, just look at this, like I put here, it will be 1 plus epsilon. so overall just this overall represents epsilon extraction factor. so you will get this xbr is equal to xbf over 1 plus epsilon. so I just want to rearrange it further to get something called fraction of B unextracted. This XBR over XBF will give me this fraction, like fraction of B unextracted, that fraction of B or mass ratio of B in the raffinate over mass fraction of this mass ratio, not mass fraction, sorry, mass ratio of this B in feed. So XRB over XFB will be equal to 1 over 1 plus epsilon. So otherwise you can also write it like fraction of B extracted. So how you will write, this is fraction of B unextracted. If I just write it fraction of B extracted, that will be just I will reverse this equation. So it will be like XBF over XBR is equal to 1 plus epsilon. So fraction of B extracted is equal to overall 1 plus epsilon. So if this epsilon is higher in value, fraction of B will be definitely higher. So how we can just make it higher, I have just discussed that this can be made higher with the help of either you increase the value of K, or that is actually increase in terms of like how we can increase it. Either we just change our solvent which we are bringing for this extraction, or we just change the conditions of the solvent, available condition, like we change the temperature, pressure. So this will also change this K. And then there is ratio of this S over FA. If I just increase this ratio, how we can increase, like either we increase this S or we increase this carrier in our feed. So that case also will help us to increase that B extracted. So we can use this equation further for calculation, or when we are going to design this system. So this is final equation, and all other equation in between are also helpful, especially just remember these two equation like 4.35 and 4.36. They are helpful to solve various problems. Overall, if I just summarize up to here, we have discussed the system in which two solvents were immiscible, completely immiscible. They were completely insoluble in each other. So we just considered that feed which contain carriers or solvent A and solute B, we bring it in contact with the new solvent C, and then after extraction or liquid extraction, they are just separated into two stream. One is extract phase and other is like raffinate phase. So out of those, we said that actually B gets distributed between these two, and we applied mass balance on this B in terms of mass fractions, mass ratios X capital, and at the end of the day we have reached to this equation, final equation. Like we have to calculate if we are looking for fraction of B unextracted, so that is the equal to simple 1 over 1 plus epsilon, or if you want to calculate fraction of B extracted, so this will be 1 plus epsilon. So here we have one example, as in the start I have told you that this is chapter 4 and section 4.4. In that we have this example 4.6. so we are going to quickly solve it here. So single stage extraction of acetic acid. So let's go through this problem. So here he mentioned that methyl isobutyl ketone C is used as a solvent. So C in actually in last section we have just discussed that the C, we are represented externally introduced solvent with the C. So he is saying like methyl isobutyl ketone, it means this is solvent which we are introducing to this system. So that is used to remove acetic acid. Acetic acid is represented with B, and B was our solute. So here acetic acid is solute. So this methyl isobutyl ketone is used to remove acetic acid from 13,500 kg per hour of the feed of 8 weight percent acetic acid. So here he has provided acetic acid in water, and water is represented with A, that is the carrier, that is part of the feed which is present in large amount. So overall flow rate of the feed is given to you here, that is 13,500 kg per hour, and that contains 8% acetic acid. You just bring this feed in contact with methyl isobutyl ketone so that you can remove acetic acid from this feed towards this methyl isobutyl ketone. Because distillation requires vaporization of large amount of water, we are using liquid extraction and not going for distillation. We have discussed somehow same example in this first lecture when we started with this liquid extraction, and there we said that when you have more than 50% of the water in the system, so these distillation and such system are not suitable. Why? Because we said we have to remove very large amount of the water. If you remember in that first example we discussed that acetic acid has boiling point of 118 degrees C, while water has boiling point of 100 degrees C at atmospheric pressure. So in that case definitely you have to like vaporize water if you are going to for distillation, because water is lighter component as compared to acetic acid. So you will be removing it, you will be heating it and separating from acetic acid. So in that case that is very expensive process that requires very large amount of heat. So we don't go for that, we are going for liquid extraction. So if raffinate is to contain raffinate, that stream which is rich in water now, and just for the sake of convention as we followed from the start, you can say raffinate mean that the lower stream coming from this liquid extraction unit. So that contain 1 weight percent acetic acid. That means now when it is coming out, it will only contain 1 weight percent acetic acid, and other 7 weight percent acetic acid is actually transferred to this new solvent. Estimate the kg per hour of the solvent needed for a single equilibrium stage. Here we have to just calculate amount of the solvent needed for this single equilibrium stage. If C and A are assumed to be insoluble in each other, this is actually application of just which we have discussed so far. The two solvents A and C are insoluble in each other, so you have to calculate in that case the amount of solvent. From experimental data in the literature, K dB is equal to 0.657. that distribution coefficient is given to you, distribution coefficient is K, and that is 0.657. Now you understand this, that your feed contain two component. What are those component? That is water and acetic acid, and you are introducing methyl isobutyl ketone in this system. This is single stage operation in which you are bringing them in contact, and initially your feed was 13,500 kg per hour, that was 8% acetic acid, and you have to remove like this, and at the end of the day it will be like only 1% in your stream, leaving as a raffinate, and other 7% is transferred to your methyl isobutyl ketone. But we are supposed to calculate how much solvent will be introduced in this system. So you are also given this distribution coefficient. So just you have just studied various equations, so you can look at those equations. So in this case any equation you can use out of those, maybe if you have other information. So the most suitable equation here, by the way, is this: epsilon is equal to K S over Fa. What we are looking for? We are looking for S, solvent flow rate, and this epsilon maybe we can calculate, we will just look at that. Then this K is given in the system as well. Fa, you know, it is given in the system. How it is given? You know that there is total flow rate 13,500 kg per hour, and that is out of that flow only 8% is acetic acid, so 92% will be your water. This is flow rate of our carrier, so it will be like Fa will be equal to 0.92 of 13,500. so just solve it please. So it will be like 0.92 multiplied by 13,500. so overall from here you can get Fa. So K is also given. Now only problem in this equation is to find epsilon. Can we find this? Do we have any equation for this? Yes, we have. So let me go back to that equation. I just forgot to put it here. So which equation we can use? Just look at these equation. Actually this epsilon is part of two equation, like this 4.35 we are already using it. We have to calculate S from here, so we can't calculate actually epsilon from this equation. So now I have to look for other equation, that is this equation 4.36, and in this equation you can see that if we want to calculate this epsilon, can we calculate? Just look at these terms. If we know these two terms, otherwise I can calculate if I know fraction of B unextracted, but that I don't know. So here from here I can just calculate this XBR and XBF. So if you remember, we just defined XBF in the start. XBF was actually mass of, this is mass ratio of B. So with respect to your A carrier. So XBF we have defined in the last slide before this. So just look at that main equation. So overall XBF, if I write, if XBF here will be equal to mass of B in feed divided by mass of A in feed. So mass of A in feed as well as mass of B in feed is known, you know already. So you can calculate this XBF factor. I think it's clear to you. So that can be easily calculated because we have overall flow rate 13,500. Out of that 8% is acetic acid. So B is acetic acid. Here it will be like mass flow rate of acetic acid in the feed stream divided by mass flow rate of carrier, that is water, in feed stream. So this you can calculate. And then other part which we need here, that is XBR. So if I need XBR, so what does this mean? That is flow rate of acetic acid in retentate stream divided by flow rate of water in retentate stream. Do you know these? Yes, we know flow rate of acetic acid in retentate stream, that is only, like he said, that is 1%. So 1% left out of like other that was coming from main initial system. So divided by mass flow rate of raffinate. So in raffinate, sorry, mass flow rate of your carrier in raffinate. So that is water which was initially coming, that does not get soluble with the other stream. So here you can see like it will be 92% of the entering that will also be leaving from this system. So overall now you know all these XBR and XBF, so that can be used to calculate epsilon, and from that equation, now when you calculate epsilon, you can come to this equation, and finally what you will get here is S, because now no other terms is missing. Like FA we have already seen from here, KD was given, and epsilon I've just talked about, it can be calculated from equation 4.36, and in this equation 4.36 actually you need two terminologies, and they can be easily calculated from the given information. So overall just calculate all these and look for answer. Finally you will get the value of S, flow rate of the solvent, and when you have solved it, just you can compare it with the solution provided in the book, because this is example, so you can just compare it with that. Okay, from here we have to start those systems which are actually in which your solvents are immiscible, A and C, as we have talked about this. This is the slide which you have already seen, that we started with two systems. One system was when your solvent A and C are mutually insoluble, they are not soluble in each other, but here we are going to start with other system in which A and C are partially soluble in each other. This diagram I have already explained, in which you introduce your feed as well as you introduce your solvent, and then you get them distributed in such a way that like this solvent A becomes somehow part of the extract stream which is rich in C, but that will contain some amount of this A, and as well in raffinate stream that is rich in solvent A, but that will also contain some part of C. So these are called partially miscible system, in which your solvents are also partially miscible in each other. Due to this, they are carrying each other along their rich streams. So this is the system. I will hopefully just finish here the lecture, because from here we have to continue by tomorrow, inshallah. So this system, just remember from here, actually I am just explaining it because in the system which we have just studied so far, that was mutually insoluble, that you will come across very few, but mostly you will have such system which are partially soluble. So at least now you know the base case in which they are mutually insoluble, but now when we look for partially soluble, can we use the same equations which we have just discussed so far? No. The reason is like if you recall the equation just we have discussed, I mean this epsilon and k and that stuff. So in that you see that they were far mutually insoluble system, and when we derived that equation we involved some terminologies which involved like this in which this A was coming from feed and that was only going to raffinate, and this C was coming from this stream and that was only going to extract. So if they are going to both side, definitely equation become complex. So we don't have equation, but we have here another system or another way, that is triangular diagram. So we can use those triangular diagram to make such calculation. So we will just start our lecture from here tomorrow, that how we can use triangular diagram and what are those triangular diagram. So if I just summarize the lecture which we have discussed so far, that initially we started with this, that when we are going to design liquid liquid extraction system, design equation system. So in this you will go for equilibrium data, and in equilibrium data we said that when we look at the equilibrium for distribution of solute between two solvent, then distribution law holds, and that distribution law give us some constant k, that is the ratio of concentration of solute in extract to concentration of the solute in raffinate. So then we said that when we bring ternary system like your feed, that is consisting of one solvent, carrier and solute, means solvent and carrier is same thing here. So solvent as well as solute that we bring in contact with another solvent. So there are various cases possible, and out of those various cases we said that two are most common. One is like when your both solvents are completely immiscible, and other when they are partially miscible. So we started with some equation or system, sorry, in which they were completely immiscible, they were completely insoluble, and we have derived one equation, and then we use that equation that can be used for designing. Sometime you have to calculate like amount of this solvent epsilon, so they will be used somehow in design of those system which are in which solvent are completely immiscible. So at the end we just said that in most of the system you have such solvents which are somehow partially miscible. So for those system, those equation which we have discussed so far are not valid, so we have to look for some other equation or other system, and other way is to use this triangular diagram. So we will just start next from here. Thank you.